Welcome to another exciting educational video brought to you by Up Vision Concept Academy. We'll be looking at physics, and our topic for discussion today is motion. Motion. This topic is tailored towards those who are preparing for WAEC, NECO, GCE, and JAMB exams. Now, what is motion? Motion involves a change of position of a body with time. It also involves how things move and what makes them to move. On the other hand, kinematics is the description of how objects move without regard to the force causing them. Normally, motion will involve a body moving. Let's say a body A moves from point A to point B. Okay, let me call the body object. So the object moves from point A to point B. Understand? Something is actually pushing the body to move. But motion is actually the study of how the body changes position from this position, point A to point B. Understand? And it also involves a time factor because it will take time for this body to move to this body. So from this body to move from this point to this point. Understand? So there are types of motion. There are types of motion. Types of motion. One, we have the random motion. Two, we have the translational motion. Three, we have the rotational motion. And four, we have the oscillatory motion. So all the motions that we know generally can be classified under this broad topic. Now, for random motion is like a zigzag movement. So if I have this body now, it goes like this, comes like this. I'm drawing the path that the body moves. So this is random motion, a zigzag movement. Understand? An example of such a motion is the Brownian motion in gas. You see that particles inside the gas, when it's observed under high definition lens, you will see that the movement of the particles inside that containing vessel is in this kind of motion, the zigzag motion. A translation motion, on the other hand, translational motion, on the other hand, is actually the motion of a body from one spot to another on a linear form, like this one now, for instance. It moves from one point to another. So when a rigid body, you understand, moves from one point, point A, to another point, another space in point B, without rotating, without spinning, it just moves, it just changes, it just goes on a straight line. You understand? This is translational motion. Now, rotational motion is when you have a body moving around a fixed point. So it has a pattern, a regular pattern around a fixed point. So if this is the point, and this is the body here, for instance, the body now starts moving like this. Understand? Maintaining relationship, with this point, the constant distance from this point. So the body moves round like this. So if this is the center point, and this is the starting point, distance between here and here can be, maybe reduced. Understand? And as the body is moving like this, you understand, it's actually moving in reference to this point, and there's actually an angle it creates. The angle that it creates anytime it moves, if it's at this point, that is the angle it creates. This angle is called angular displacement. It's actually displacement, like a distance. So it's moving by angles. So it's moving like this, and in reference to this point, there's an angle it creates. If I go this point again, I see another angle again creates. Understand? So this one is called the rotational motion, and it's the kind of motion that the body moves around a concentric circle. It creates that the path that the body moves is actually the radius, the circumference of that circle. And finally, we have the oscillatory motion. This motion can be seen in the motion of a single pendulum. So if I have rigid place objects here like this, and I put a swing here, a, a, a wire here, and at the bottom, at the point of it, at the end of it, you tie a ball, a small ball, and then you take the ball to this edge. You understand? Take it to this edge. This is where the ball is now, the new position. Then when you take it to this edge, you leave it. You leave it. So when you leave it, it goes here, past this point, and still continues. You understand? When it gets to this point, it stops, it goes back. So the movement that occurs from the periodic movement from point to this point, from this point to this point, is known as the oscillatory motion. So it oscillates about this point. It oscillates about this point. So at this time, you know that this is the length of the pendulum, and this is the angular displacement. The angular displacement. So actually, this motion is seen in simple pendulum. Also, we can see this kind of motion in a spiral spring. A spiral spring where you have a spring like this, and the mass is here. This is the mass. You understand? This is the mass. So if I just take this mass like this, draw it down so that this string can extend. You understand? When it extends, if I just release the mass, it will start going up and down. So this one too is to and fro movement, but its own is up and down. It goes up and it comes down. It goes up and it comes down. This is actually derived from Hooke's law. This is Hooke's law, where this is the force and extension and the constants. So this is from Hooke's law. So we'll look at that later in this subject, in this course. So you see that the force that's applied is directly proportional to the extension, provided that the elastic limit is not exceeded. Okay, so we are concerned about the motion, not the force now, please. I'm just putting this one so that when we come to Hooke's law, you will see the force that is, we're analyzing the force. But now we're analyzing the motion that happens when you release a mass under a spring, tied to a spring. When you drag it down and release it, it goes up and down, up and down. That up and down motion is what they call the oscillatory motion. So it is actually oscillating about a point. So these are the two forms of oscillatory motion. So we go to quickly the next subtopic of discussion: relative motion. Relative motion. Relative motion. Relative motion. So the concept of relative motion is two bodies, or that you are considering motion between two bodies. If a guy is walking on the street, it's moving actually, it's moving, but somehow his movements and every particular point is relative. It's assumed that maybe if he comes to this point is fixed. So his movements towards this point, you understand, is relative, meaning that as it's moving, the distance between here and this point will be reducing until he passes it. When you get to this point, it's the same, they are the same place. When he passes it, also the distance also, so it's relative. Sometimes a car can start a journey. A car can start a journey. I'm trying to just explain the concept of relative motion. Can start a journey, and let's call this one car A, and a car B here. Let me use another phone, maybe a Jeep or something. You understand? So this is it. So if this one, the speed is slower, let's say this guy is moving at 60 kilometers per hour, and this guy is moving at 100 kilometers per hour. So which one is moving faster? This one is at the back, right? This one is in the front, right? And this point is in the front. This guy is moving faster. A point will come when this guy will pass this guy. When car A will go past car B. Now that point where, as in, there's a, if you are inside this car A, you understand? There's a way you are seeing the people inside here. It's as if you are coming close. So when you pass them, when your car go past them, you see that there is a relative motion. Let's see a way I can describe. You can describe the motion of this related to this. Relative motion is just like the motion of two bodies. You understand? Of two bodies, one related to the other. One appears to be fast, one appears to be slow, one appears to be stagnant at every point in time between two. But even if the body you are walking on, maybe to the ground, is static, you that are going that is going on it, you are actually having a relationship with that stagnant body. You understand? So we may define motion as a change in position. So it will never be impossible for us to determine the change in position without a point or frame of reference. So there's also a frame of reference. This guy walking on this ground now, the reference is the ground or this point A. Understand? This guy that's trying to overtake this guy, the reference is this guy. A time will come when at 400 kilometers per hour, he will overtake this guy with 60 kilometers per hour. But that time will come. So there's always a reference. And we assume that, there is a point of rest, or the other bodies at a point of rest. So every measurement must be made with respect to such a point or frame of reference. Now, another term I want to talk about is displacement. Displacement. Displacement is like you are saying that is the distance traveled in a specified direction. So if, for instance, now a guy, this same guy, moves 40 kilometer east, 40 kilometer eastward. This is now. And when he got to this point, he now moved 30 kilometer north. What is his displacement? What is his displacement? So displacement is not first of all, he moves east and then he moves north. That's the description for you to get the displacement. But displacement is defined as the distance traveled in a specified direction. So for us to get displacement, we'll just use one magnitude, one particular distance to get it, one particular magnitude to get it, one particular length to get it. And that length is gotten by resolving this component of his displacement or of his movement to this component of his movement. So if I apply Pythagorean's theorem now from this is one side, this is hypotenuse. Now this angle, this line is gotten by squaring this, adding two values together, find the square root. The answer is 50 kilometers. But if I want to describe this guy's displacement, I will describe this guy's displacement using this one and using the angle, the directional angle that he uses. So I can come and say that the boy walks, that the displacement of the boy is what? 50 kilometers northeast. Why? Because I went north and I also went east. Understand? The description is not east now. At this point, this is the guy's coordinates. This is the guy's coordinates. This is where he started from. So I'll put a coordinate there. So this is north, this is south, this is west, and this is east. You understand? So this is where he started from. So if it moves like this, say when it moves like this line, what does it mean? What does it mean? It is actually going northwards and eastwards. That's why I say displacement for my guy is 50 kilometers northeast, NE. So displacement actually gives you a particular direction, a specified direction. All right. So the next one we look at is the speed and velocity. Speed and velocity. Speed and velocity. Okay. Speed and velocity. So speed. There's one guy called Speed in the internet. The guy is just doing many stunts, jumping over moving cars and jumping up into a moving train. But this one is speed in physics. So speed is the rate at which a body covers its distance. So speed is the rate at which a body covers a distance. So this is speed. Is the rate at which a body covers a distance. This is covers a distance. Okay. So speed by formula is equals to distance over time. This is the formula for speed. The SI unit for speed, SI unit, we talk about SI unit in measurement, is meter per second. Meter per second. So when you are calculating, when you finish, your answer will be in this units, meter per second. All right. So now that's for speed. Now uniform speed is when a body covers equal distance in equal time interval. So uniform speed is when a body covers equal distance in equal time. Equal distance in equal time. This one is uniform speed. So it's still a meter per second. There's something different from that one, just that the rate of change of distance to time is constant. Now, velocity is the rate of change of displacement. You know, we define displacement as particular direction. So when they are saying a body is going so and so northeast, that's displacement. The difference between displacement and distance is that displacement is directional, while distance is not. It's not. Distance can just be anything, can just be any description of any direction. But when you talk about the displacement, it is a particular direction. So velocity is described in terms of displacement. So it's the rate of change of displacement, delta displacement. This is the definition. Delta displacement over delta time. What's delta? Rate of change. Delta displacement over delta time. Okay, so I will quickly take before I take anything, velocity and speed, what is the difference? Distance over time for speed, velocity, displacement over time. So this one has vectoral attributes. This one have a scalar attribute. The distance is scalar, while this one is vectoral. Okay, so example. Let's take one example. Okay, example. Okay, so it says a car travels at an average, this is A for average speed of 100 kilometers per hour. What distance does it cover in 5 minutes? Okay, so what does it cover in 5 minutes? So the guy is going at 100 kilometers per hour. So what distance does it cover in 5 minutes? Okay, so that's a question for us to ponder about. Now, if you look at it critically, we are given what are we given? We're given speed. Speed is what? 100 kilometers per hour. And time is what? 5 minutes. 5 minutes. So we're looking for distance. What's the formula? Speed is equal to distance over time, right? So speed is equal to distance over time. This is simple enough, but the problem now is that the units, you have to look at the units. They want us to get our answer in, we can convert all this to meter seconds and you know your conversion, you can convert it to seconds. Yes, to seconds. This is minutes. So you convert it to seconds. Okay. So Okay, so distance what we're looking for. So the making distance subject, distance will now be equals to speed times time. What's the speed? 100 kilometers per hour. And the time is 5 minutes. So, but 60 minutes make 1 hour. So we will convert this one to hours. Convert this one to hours. So if this speed is already 100 kilometers per hour times the time is 5 minutes, but in hours, how many hours is in 5 minutes? It's just 5 over 60. That is it. That is it. So at this point in time, we can get our distance as 8.3. By the time you compute this, 8.3 kilometers. So you see what's happened here. The formula is easy to get, but you see that we need to ensure that this unit, this time is in hours, not in minutes. So we'll convert 5 minutes to hours. Okay. So the next one we'll look at is acceleration. 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 Let's look at acceleration quickly. Acceleration. So acceleration is defined as the rate of change of velocity per time. Acceleration is defined as the rate of change of velocity per time, unit time. Okay. So the what's it called? The units for expressing it is meter per second square. So by formula, acceleration is equal to change in velocity over time, where A is acceleration. See, in physics, when you are writing theory courses, theory section, break a formula like this and define it. Use notations. A is acceleration, but define it here. They will know what you are saying. V is final velocity. Final velocity. U is initial velocity. And T is what? Guess. Time. You got right. So this is acceleration. If you define it like this in the exam, give your definition in words, put the units. The unit is, let me just put it well for you. The unit is in meter per second square. Then go ahead and define it in formula and define the parameters by saying that A is this, B is that, and so on and so forth. Okay, so even from here, we can even say this one, it implies that final velocity V is U plus AT. If you make it subject to formula, come check out our math videos where we do the transpose. So you will make subject to formula by doing this. Okay. So we have talked about acceleration. Let's move on to another important aspect of this kinematics motion. Let's talk about velocity time graph. Velocity time graph. Okay, you will see it often. Velocity time graph. Velocity time then graph. Okay, so velocity time graph. So it's actually graphical representation of the relationship between velocity and time. So for instance, if I try to plot a graph like this, where this is the y-axis by convention, normally this is the x-axis by convention, positive and negative, positive and positive. Understand? Now, if we put on the positive y-axis velocity, and this x-axis we put time. That means this side, what I'm having here is in meter per second, and this is in seconds. So if a body starts from rest 0, you understand? Starts from rest 0, and gradually moves. Normally it comes from a table. Okay, let me just draw a table and let's plot the graph. I'll draw a table under. Let me draw a table under. You can see it. Okay, so there's a table where different results was collected for velocity and time at different times. So I have at a 0 velocity, This one is in meter per second, and this one is in time, S. These are the units. Okay, so at 0, I had 0. At 5, I had 2. I will plot it. So we will know at 10, I have 4. I have 4. At 15, I had 6. At 15 again, there's 8. And at 7.5, or let me say 7, I had 10. And finally, at 0, I had 12. Okay. Now, this is how normally it's gotten. So this is the time axis. So the high point, you have 0, I have a 2 somewhere, I have a 4, I'm plotting it, 4, I have a 6, I have 8, I have 10, I have 12. I have 12. So this is time in seconds. So at the point where this time where I have 0 is 0 here. So 0, 0 is a dot here. The two coordinates are dots. When it was 2 on time, it was 5 on velocity. So let me put 5 here and let me just plot it like this. When it was 4, it was 10. So let me put 10 here. And this is how you plot graph for those of us who are doing practicals. Know how to plot graph very well. So when it was 4, you had 10. Okay, when it was 6, you had 15. So let me put 15 somewhere here. 15 is the highest. Let me just put 15 here. And when it was 6, we had 15. So you then have to close the graph. Then at the same 15, you maintain, you have 8. So I come here again, just put 8 here. Then at 10, there was 7. So at 10, it dropped to 7. So 7 is in between 5 and. So let me just do like this. Then at 10, then at 10, I had 7. At 12, I had 0. So this is 0. So if you want to put the point, just follow where the line touch, like this, like this, like this. So this velocity time graph, this is how it comes. It actually comes from when a range of data is created between velocity and time. So when the time was 0, what was velocity? It was 0. The body started from rest. Is what you are measuring from when the body was already moving. That's when you will have a value here. Understand? So when it was 2 seconds, what was velocity? It has increased to 5. When it was 4 seconds, it was 10. When it was 6 seconds, it was 15. When it was 8 seconds, it was, at this point where velocity was constant, when time changed, this was where there was uniform velocity, no acceleration. Acceleration comes when there's a slope. When it comes that velocity remain constant and time change, then acceleration was 0. At this point, let me label it. This is O, then A, B, C. At this point, AB, acceleration was 0. Then when you start coming down again, you have a deceleration. So this is velocity time graph. It's just a graphical representation of relationship between velocity and time. As time is changing, velocity is not changing. Sometimes they can start teaching from like this. They can start like this, from this point. Now went down, bam, like this. So that means at point 0, at time 0, there was already an existing velocity. There was an existing velocity. There was initial velocity when it was 0. That means the capture was done while the body was in motion. You understand? That is for that cases, for that kind of case. Okay, so let's move on. Let's move on. So acceleration is actually the slope. If I want to check, okay, let me erase this thing and make it without all this values on it, so that I can just define some key terms. So if I have it like this, We all know how it was gotten, but let me draw it without the figures. Without the figures. So it's like this, then like this. Okay, so let me just do this one like this. Okay, so if this is O, A, B, let me put something here. Let me put C. Let me put D. Let me put P and Q. Now, from this time graph, velocity time graph, we can see that acceleration, acceleration is the slope of the graph, which is AP over OP, line AP over line OP. This acceleration, acceleration, deceleration is line BQ over line QD. This one is always negative. It's negative because it's negative acceleration. So BQ over QD is always negative. It's always negative. It's negative. You can call it deceleration or retardation. Okay, so we're going to look at an example and wrap up this. Okay. All right. So most of the time they will give you this velocity time graph and ask you to find the direction. They can give you something like this, like a car is moving at so and so velocity. So it attains. Okay, let me have it. Let me just put it down so that we can consider it quickly. Okay, it's a lengthy one, but I'll put it down on the same. You see, a car starting from rest accelerates uniformly and attains a speed of 80 meters per second in 30 seconds. It maintains this speed or this steady speed for another 30 seconds. Okay. Then it slows down uniformly until it comes to rest. Okay, in the next 40 seconds. Okay. Then you say sketch. That's the first question. Sketch the VT graph. VT graph, velocity time graph. VT graph for the motion. Okay, I will stop here in this question. The other question is to find the acceleration and the retardation. Okay, so let me just stop here so that I can have space to draw the graph. You see, a car starts from rest and accelerates uniformly and attains a speed of 80 meters per second. So, see, you are drawing a graph. So, actually, you have this like this. You're drawing a graph. This velocity, a meter, seconds, and this time in seconds. Now, I say a car starts from rest. Rest is 0. And accelerates uniformly. So that means there's a slope like this going up. Understand? Until it attains a speed of 80 meters per second in 30 seconds. So at 30 seconds here, it attained a speed. The speed is 80 meters per second here. So this is what it attained. Then I said, then it maintains this steady speed. So it was steady here and it maintained it for the next 30 seconds. So from here to here, 30 is 60. You understand? Next 30 seconds from here to here. You understand? Just make sure you follow how the question is going. So 30 seconds. Then it slows down and uniformly until it comes to rest. Slowing down means that at this point, it goes down like this until it comes to rest. In the next 40 seconds. So 40 seconds from here is 100. Please just know how you put your values. So it says at 30 seconds, it attained the speed. Next 30 seconds, it maintained the speed. Then next 30 seconds, it went down. So the total time it will move for 60, 100 seconds. That's when it moved. Total time of movement. Now, they say sketch the velocity. So you have sketched it. You can do well to label it so that you can use that labeling to refer to any question they want to ask. So they say you should sketch. You have sketched it. Second question here, I will read it out. Please just listen attentively. It says sketch. Then it says the motion of this car obtained from the graph the uniform acceleration during the first stage of journey. So they say you should, from this graph, obtain the acceleration. Acceleration from the graph is what? Change in velocity, which is OA. Acceleration is OA over, not OA. Let me put something here. A, B, C, D, E, and F. This point is E. So this line over this line, change in this line. This line here to here is here. So change in velocity over change in time. AE, line AE over line EO. This is acceleration. Please, acceleration is defined as change in velocity over change in time. Change velocity is this side now, this line. This is the line. So here is the corresponding dimension to this one. So this one now is AE, line AE, and the time is here, line EO. So what is AE? AE is what? 80. 80, and EO is what? 30. So acceleration is 8 over 3 meter seconds square. 8 over 3 meter seconds square. That's for acceleration. The next question says we should obtain the uniform acceleration during the first stage of the journey, the retardation during the last stage of the journey. Retardation is what? Retardation is what? Retardation or deceleration is BF over FD. What's BF? Again, is 80. FD is what? 40. Retardation is 2 meter second square. 2 meter second square. I said before it's minus, but because we know the retardation is minus, we don't need to write it. It's minus, but as in what it means is that when I say minus, negative slope. But what it means is that if you say retardation, that means this car slowed down using this speed. It slowed down and finally got to a stop using this speed. Okay, the last one is question is asked, what is the total time? Total time is already 100 seconds from our graph. 100 seconds, because I will add this first one, 30, then 40 and 40. Sorry, 30. Here to here is 30. Here to here is 30. Here to here is 40. So everything add together is 100. Already in the graph is showing 100. All right. So I hope this has been informative for you. I'd like to thank you for viewing. Kindly subscribe to the channel if you are new, and hit the like button to support what we do. Thank you again for watching.